On some future clear night, you might step outside, look up, and realize that the most important thing in your sky is something you have never noticed before. It is not a bright star, not a planet, not even the Milky Way. It is a faint oval smudge barely larger than your thumbnail at arm's length. It looks harmless, almost boring, a soft piece of fog someone forgot to erase. Yet that tiny blur is the nearest giant galaxy to our own, a system of 1 trillion suns hanging over you in plain sight. Tonight we are going to learn how to find it, what you are really seeing and why that matters. And if you enjoy journeys that turn innocent little smudges into mind-bending truths, remember to like this video and subscribe so you can keep travelling the universe with us. Let us start with something wonderfully old-fashioned. No apps, no telescope, no star chart. Just your eyes and a dark skim. If you can get far from city lights, somewhere the Milky Way itself stretches faintly overhead, you already have the most powerful detector you need. Our target is Andromeda, and the trick is that the galaxy is hiding in a place your brain is not used to paying attention to. Once you know the path, you will never be able to unsee it. The first step is to find a shape that really stands out. Look for Cassiopeia, the constellation that looks like a crooked letter W or a zigzag scribbled across the sky. Depending on the time of year and your location, it may be high overhead or tilted to one side, but that W shape is one of the easiest patterns to recognize. Pick out the middle of the W, the central point where the shape seems to hinge. That spot is your starting arrow pointing almost directly toward Andromeda. From that center star, imagine a straight line running away from the open side of the W down toward another bright shape in the sky. That destination is Pegasus, the square of 4 bright stars that looks like a celestial window frame. Trace your line halfway from Cassiopeia toward that square. Pause there, not at any particular bright star, but in a seemingly empty patch of sky. Let your eyes relax and soften. After a few seconds, a dim, elongated blur should start to appear. That delicate, fuzzy patch is the Andromeda Galaxy. To the naked eye under a truly dark sky, Andromeda looks like a small glowing cigar of light. It is longer than it is wide and appears about the size of 2 or 3 full moons placed end to end. That is its bright inner region, the bulge and central disk where stellar light is dense enough for your vision to pick it up. Your eyes are terrible at seeing faint, extended objects, so you are only perceiving the tip of the iceberg. Long exposure photographs that collect light for minutes or hours reveal a very different picture. In deep images, especially those that capture ultraviolet and hydrogen alpha light, the galaxy stretches across roughly 5 to 6 degrees of ski. That is the same as lining up 10 to 12 full moons side by side. Old astronomy books sometimes claimed Andromeda was as wide as 30 full moons. That number came from over-enthusiastic estimates and misunderstandings about how faint outer structures blend into the background. Modern measurements still show something almost absurd. The biggest deep sky object visible without a telescope is not a tiny planetary nebula or a bright cluster. It is an entire galaxy that would dwarf everything else in your field of view if your eyes were just a little bit better at collecting light. Humans have been confused and fascinated by this little patch for more than 1,000 years. In the year 964, the Persian astronomer Abd al-Rahman al-Sufi carefully catalogued the bright stars and strange objects he could see. When he came to Andromeda, he described it as a small cloud, a faint mist that did not behave like a normal star. Chinese observers had already recorded something similar centuries earlier, noting a hazy object in that region of the sky. None of them knew they were looking at another galaxy. The very idea of galaxies did not exist yet. For centuries, European astronomers following in their footsteps also filed Andromeda away as a nebula, a cloud of gas within our own stellar system. Early telescopes showed a brighter center and a faint halo, but could not resolve individual stars. To observers in the 1800s, it looked like a glowing whirlpool or a spiral cloud caught up in the Milky Way. They were spectacularly wrong about what they were seeing, yet their drawings and descriptions were more accurate than they realized. Those sketches captured the shape of an island universe they did not know was an island. There is something almost poetic about that. When you stand under a dark sky and look at the same smudge, you are participating in a chain of human curiosity that stretches across cultures and centuries. Ancient sky watchers had exactly the same photons falling on their retinas that you do. The difference is what those photons mean in your mind. Where they saw a mysterious little cloud, You know that you are receiving light from stars arranged in a vast spiral disk, orbiting a supermassive black hole embedded in a halo of dark matter, racing through space toward us. All of that is hiding inside a patch so faint you might miss it if you blink. Finding Andromeda with your own eyes also changes the way you feel about distance. Space can seem abstract when it lives only in numbers and diagrams. 1,000 light years sounds big, 1,000,000 sounds bigger. 2.5 million feels almost comically huge. Yet those numbers stop being abstract once you can point at a specific place in the sky and say that is where those millions of light years stretch. You are no longer dealing with a story about distant galaxies in general. You are dealing with one particular neighbour, marked by one particular blur that your brain can anchor to. As your night vision improves, you might notice that Andromeda is not alone. On very dark nights, with patience, some observers can glimpse tiny companions nearby, satellite galaxies that orbit the main system as faint knots of light. Even if you never quite see them, knowing they exist makes the view richer. That fuzzy patch is not a single object. It is a whole gravitational city with suburbs and satellites and long streams of stars that extend far beyond what your eyes can catch. Standing there, it is easy to feel small, maybe even a little overwhelmed. You are a human being a couple of meters tall on a rock 12,700 kilometers across, staring at a galaxy 220,000 light-years wide. Yet you can find it with nothing but your eyes, your memory of a W and a square, and a little patience. You are not just a passive speck. You are an active observer, using pattern, story and geometry to connect yourself to a structure that dwarfs your existence. That connection is the real magic of this first step. We have, for the moment, resisted the urge to throw big numbers at you. We have stayed with the view from a hillside or a backyard, where Andromeda is just a faint smudge in a strip of stars. In the next part of this journey, we will finally start to unpack what 2.5 million light years really means, how we know that distance, and why the light in your eyes tonight began its journey long before humans existed. The blur you just learned to find is about to become far stranger than it looks. When you look at that faint smudge of Andromeda, you are not just looking far away, you are looking far back. The phrase 2.5 million light years sounds like a statistic that belongs on a trivia card, not something your brain can actually feel. So in this part, we are going to slow it down. We will translate that distance into Dusha time, into travel, into history, until it stops being just a number and becomes a story you can carry around whenever you glance at that patch of sky. First, we need to understand what a light year really is. Light is the fastest thing in the universe. In empty space, it moves at about 300,000 kilometers per second, or about 186,000 miles per second. In the time it takes you to snap your fingers, a beam of light could circle Earth 7 times. Let that sink in. Now stretch that out. Keep that beam of light racing through vacuum for a full year. The distance it covers in that year is a light year, and that works out to roughly 9.5 trillion kilometers, or about 5.9 trillion miles. 1 light year is not a unit of time, it is a unit of distance built out of time and speed. So what happens when we stack up 2.54 million of those units in a row? Multiply 9.5 trillion kilometers by 2.54 million, and you get a number that almost nobody has an intuitive feel for. About 24 quintillion kilometers. That is a 24 with 18 zeros after it. In miles, that is around 15 quintillion. You could read that number out loud all day and it would still sound like nonsense. Our brains were tuned by evolution to spot fruit in trees and predators in bushes, not to handle 24 quintillion of anything. To make that distance less abstract, compare it to something closer. Light from the sun takes about 8 minutes and 20 seconds to reach Earth. If the sun disappeared in this instant, you would still see daylight for more than 8 minutes before the darkness caught up with you. The moon is a little over 1 light second away. That means whenever you look at the moon, you see it as it was about 1 second ago. That delay is so small that your brain treats it as real time. Now move one step out. The nearest star beyond the Sun, Proxima Centauri, is about 4.24 light-years away. Light leaving that star tonight will not reach us until more than 4 years have passed. If a civilization lived on a planet there and tried to send us a message using light, every exchange would take almost a decade round trip. That already feels uncomfortably slow for a conversation. But it is nothing compared to Andromeda. Light from Andromeda takes about 2.54 million years to get here. The photons hitting your eyes when you look at that galaxy began their journey when Earth was a very different world. Early members of our genus, hominins like Homo habilis, were just starting to shape stone tools on the African savanna. There were no cities, no writing, no agriculture, not even anatomically modern humans. All of recorded human history, from the earliest clay tablets to digital telescopes, covers less than 1/4% of that travel time. Everything we think of as history fits into a tiny sliver at the end of the light's journey. This means that your view of Andromeda is literally a fossil record in light. You're not seeing the galaxy as it is now in this instant. You're seeing it as it was 2.5 million years ago. Stars have been born and died there while their light has been in transit. Supernovae have flashed and faded. Star-forming regions have brightened and dimmed. Entire clusters have drifted along their orbits. Those changes are happening in Andromeda's present, but they are invisible to us until their photons finally arrive. Right now, above your head, there is a version of Andromeda you cannot see yet, 2.5 million years ahead of the picture in your eyes. Now imagine that instead of just watching, you wanted to go there. Suppose you had a spaceship that could travel at the speed of light, which physics tells us is impossible for anything with mass, but as a thought experiment it is useful. You launch your ship straight toward Andromeda. Even at that ultimate speed limit, your journey would take 2.5 million years. If your crew somehow stayed alive that long when they stepped out into Andromeda, Earth would be unrecognizable if it existed at all. The continents would be in different places. The sun would be farther along in its life. Any trace of human civilization would be ancient geological archaeology. The reality is even harsher. The fastest spacecraft humans have actually built is the Parker Solar Probe. At its closest swoops past the sun, it reaches about 700,000 kilometers per hour, or around 430,000 miles per hour. That sounds blisteringly fast compared to planes and rockets. At that speed, you could circle Earth in about 3.5 minutes. Yet if you pointed Parker toward Andromeda and kept that top speed, the trip would take roughly 3.9 billion years. That is almost as long as Earth itself has existed as a planet. Voyager 1, humanity's farthest and one of its most storied spacecraft, travels at about 61,000 kilometers per hour, around 38,000 miles per hour, as it drifts through interstellar space. If you gave Voyager a new course and asked it to head for Andromeda, the journey would take more than 44 billion years. That is over 3 times the current age of the universe. By the time it arrived, not only would Earth and the Sun be gone, but the cosmos itself would be in a completely different phase of its evolution. In practical terms, Andromeda is forever beyond the reach of our current style of travel. So when we say Andromeda is 2.5 million light-years away, we are quietly saying several things at once. We are saying this galaxy is so distant that light itself needs millions of years to cross the gap. We are saying any physical journey at human-scale speeds would take longer than the lifetimes of stars. We are saying that every time we look at it, we are doing time travel with our eyes, sampling a frame from a cosmic movie whose later scenes we will never watch. There is a strange comfort in that. The distance between us and Andromeda is vast enough that nothing happening there tonight can harm us, and nothing we do here can touch it for millions of years. Yet the photons arriving now carry a detailed record of what that galaxy was doing long before our species appeared. By learning to decode those photons, we turn an unreachable place into something we can understand and even predict. In the next part, we will zoom in on Andromeda itself. Now that we have some sense of how far away it is and how long its light has been in flight, we can ask a new question. What exactly is this thing that looks so small in our sky, yet takes a light beam millions of years to reach? We will explore its size, its mass, and the monster that waits at its core. We have stood under the night sky, found that tiny smudge, and stretched a mental tape measure across millions of light years. Now it is time to ask a new question. What is this thing actually made of? When you say Andromeda is a galaxy, that word can feel abstract, like a label on a box. In this part, we are going to open box. We will pull out its size, its star count, its mass, and then dive into the crowded, dangerous region at its heart where a black hole weighing more than 100 million suns quietly waits. Start with the simplest number, the diameter. Andromeda is about 220,000 light-years across. That means if you could put the Milky Way next to it, our home disk of roughly 100,000 light-years would look noticeably smaller, maybe 2/3 of Andromeda's width. A single ray of light, travelling at that universal speed limit, would need more time to cross Andromeda's disk than modern humans have existed on Earth. Our entire species fits inside a single crossing time of this one galaxy. The shape that light would pass through is a barred spiral. If you could look down from above the galactic North Pole, you would see a bright central bulge like the yolk of an egg, with a straight bar of stars running through it. Out from the ends of that bar curl great spiral arms, sweeping around the disk. Those arms are not solid structures, but patterns of higher density. Dust lanes thread through them, star-forming regions glow along their length. And older stars fill the space in between. Surrounding all of that, extending much farther out, is a faint halo of stars and globular clusters that we will explore more later. Now pack that structure with stars. The best estimates put Andromeda's stellar population at roughly 1 trillion individual suns. The Milky Way holds something like 100 to 400 billion. So Andromeda may have 2 or 3 times as many stars as our galaxy. Perhaps more, depending on how you count the faintest ones. 1 trillion is another number our intuition fails on, so let us translate. Imagine you stand in front of a screen and start counting stars in Andromeda out loud at a steady pace. 1 star per second. No breaks, no meals, no sleep, no weekends. After 1 minute, you have counted 60. After 1 hour, 3,600. After 1 day, a little over 86,000. If you kept going at that pace, never stopping, you would need around 32,000 years to reach 1 trillion. That is longer than the time between the first known human cave paintings and today. The number of stars in this one galaxy casually outstrips the whole span of human culture many times over. Those stars do not all weigh the same. Some are tiny red dwarfs with a fraction of the sun's mass. Others are blue giants with dozens of solar masses. When astronomers talk about a galaxy's mass, they use the sun as a measuring stick. Add up the mass of all the stars, all the gas, all the dust, and you get a number around 1.5 to 2 trillion solar masses for Andromeda when you include dark matter. The visible components are only a minority of that total. Most of the gravity comes from something we cannot see, a dark halo that surrounds and supports the bright disk. We will dig into that dark skeleton later, but even focusing just on the ordinary matter, we are already dealing with an object that weighs like 1 trillion suns. The central bulge is where much of that visible mass crowds together. This swollen, football-shaped region spans roughly 30,000 light-years. That is about 1/3 of the entire diameter of the Milky Way packed into Andromeda's core alone. The stars there are predominantly old, reddish and closely packed. In our neighbourhood, the nearest star beyond the Sun, Proxima Centauri, is over 4 light-years away. Near Andromeda's centre, average separations can be measured in fractions of a light-year. If you lived on a planet in that region, assuming it could form and survive, your night sky would never be dark. Thousands of stars would shine bright enough to cast shadows. The combined starlight would bathe the sky in a permanent cosmic twilight. Buried inside that glare is the real monster. At the exact centre of Andromeda lurks a supermassive black hole with a mass of roughly 140 million suns. For comparison, the black hole at the heart of the Milky Way, Sagittarius A star, weighs in at about 4 million solar masses. Andromeda's central black hole is around 35 times more massive. In everyday terms, if the Milky Way's black hole is a mountain, Andromeda's is a small continent collapsed into a point. Right now, that black hole is relatively quiet. It is not greedily devouring large amounts of gas, so it does not blaze as a quasar. But quiet does not mean harmless. When an unlucky star or gas cloud wanders too close, the tidal forces near the event horizon stretch and rip it apart. The shredded material spirals into an accretion disk, heating to millions of degrees. For a while, that disk can outshine the rest of the galaxy in high-energy light. Jets of particles may fire from the poles at nearly the speed of light. Eventually, the fuel runs out, the flare dies down, and the black hole goes back to dozing. On cosmic timescales, these feeding episodes can switch on and off many times, turning the galactic core from serene to violent and back again. For years, astronomers thought Andromeda might harbour not just one, but the 2 supermassive black holes. High-resolution images showed a double nuclear structure, 2 bright peaks near the centre rather than one. It was natural to imagine a pair of fused galaxies, each bringing its own central black hole into the mix. A binary black hole system that massive would be an astrophysical jackpot. But as better instruments and more careful analysis arrived, that picture changed. The current view is more subtle, and in some ways more interesting. Instead of two separate black holes, there seems to be a single supermassive black hole surrounded by an eccentric disk of stars. Their orbits are not nice, neat circles centered perfectly on the black hole. They are stretched ellipses, with their closest approach offset from the exact center. When you look at many of these orbits at once projected onto the sky, the starlight naturally piles up in two bright regions. The so-called double nucleus is not two monsters but one, wrapped in a skewed, swirling swarm of stars that creates an optical illusion. This little mystery and its solution tells you something important about galaxies. Even when you think you are seeing clear, solid structures, you are often seeing patterns that emerge from countless individual orbits and interactions. Andromeda's core is not a static jewel mounted at the center of the disk. It is a churning three-dimensional volume where gravity from the bulge, the bar and the black hole all combine to shape the paths of stars in complex ways. What looks like a simple bright dot in the middle of your backyard smudge is, in reality, a deep gravitational well lined with entire suns, whipping around at hundreds of kilometers per second. So now we have a different mental picture of Andromeda than the one we started with. Not a vague fuzzy oval, but a barred spiral about twice the width of our own galaxy, filled with roughly 1 trillion stars, anchored by a bulge tens of thousands of light years across, and ruled at the center by a black hole more than 100 million times the mass of the Sun. In the next part, we will trace the spiral arms themselves, follow the waves that shape them, and watch how this giant structure turns gas into new stars along its sweeping lanes. From a distance, Andromeda looks like the textbook idea of a galaxy. A bright center, a bar of stars, and graceful spiral arms curling out into the dark. Those arms are so iconic that it is tempting to think of them as solid structures, like the arms of a spinning pinwheel toy. In your mind, you can picture the whole disk rotating like a rigid plate, dragging its arms along. It feels intuitive. It is also wrong in a very interesting way. The stars in Andromeda do not move like paint on a spinning record. The galaxy is a collection of individual orbits, each star following its own path around the center. Near the core, orbits are tight and fast. Farther out, they are slower and more leisurely. If the arms were literally made of the same stars holding hands as they went around, the different speeds would twist the pattern into a tight spiral mess in only a few 100 million years. Yet when we look at Andromeda, the arms are still there. Not perfect, not frozen, but recognizably spiral. The solution is to stop thinking of the arms as things and start thinking of them as waves. Astronomers describe them as density waves, ripples of slightly higher density that move through the disk. A good analogy lives much closer to home. Picture a ring road or a circular freeway. Cars move around the ring at different speeds, but sometimes you hit a region where traffic slows, bunches up, and then speeds up again. That region of congestion travels along the road as a pattern, even though the individual cars that pass through it are constantly changing. The jam is real, but it is not made of the same cars all the time. Spiral arms work like that. The density wave is the traffic jam. Gas clouds and stars are the cars. As the wave passes through a region of the disk, it gently squeezes the gas. That compression is enough to tip some molecular clouds over the edge and trigger gravitational collapse. Cores within the clouds shrink, heat, and ignite. New stars are born. The density wave keeps traveling, but the stars it leaves behind continue along their own orbits, leaving a trail of bright young light marking where the wave passed. The most dramatic of these newborn stars are the massive O and B type stars. They are hot, blue, and unbelievably bright, each one shining thousands or millions of times more intensely than the Sun. They blaze so fiercely that they pour out ultraviolet radiation, carving glowing bubbles in the surrounding gas. To our telescopes, these regions show up as sprawling red and pink emission nebulae, the neon signs of fresh star formation. Because these massive stars live fast and die young, they do not get far from where they were born before they explode as supernovae. So the spiral arms end up lit by clusters of short-lived blue giants and their glowing neighbourhoods. Look at Andromeda in blue light and the pattern jumps out. The arms form luminous lanes dotted with clusters, associations, and H2 regions. But if you could turn off the light from young stars and see only older populations, the arms would be much less obvious. Those older stars are everywhere, filling the disk. The spiral structure we love in photographs is really the tracer of star-forming waves, not a fixed skeleton of the galaxy. That difference has an important consequence. It means the pattern can persist for billions of years without winding itself into a knot. The density wave moves at its own speed, set by the gravitational pull of the disk and the bar, while the stars and gas orbit faster or slower depending on their distance from the center. The galaxy is like a gigantic musical instrument where gravity keeps exciting the same spiral motors over and over, even as the individual notes change. Andromeda's spiral pattern is not perfectly balanced. One side of the galaxy looks more prominent, its arms clearer and more extended. The other side is disrupted, with segments that look less regular. For a long time, this asymmetry was just an observational curiosity, a detail in images. Now, combined with deep surveys and computer simulations, it tells a story about Andromeda's past. Roughly 800 million years ago, long before humans existed, Andromeda experienced a major encounter with another substantial galaxy. This was not a gentle flyby. It was a merger, a smashing together of two large systems of stars, gas, and dark matter. The intruding galaxy did not survive in its original form. Its stars and gas were stripped, wrapped into streams, and absorbed. But it left fingerprints all over Andromeda's structure. One of those fingerprints is the lopsided spiral pattern. When a big companion plunges through a disk, it yanks on the stars and gas, amplifying some spiral modes more than others. The resulting pattern is not the tidy two-armed spiral you might see in a textbook drawing, but something skewed. One arm may be thicker or more extended. The disk may warp, one side flaring or bending. These distortions do not snap back quickly. They can linger for billions of years as the system slowly relaxes. Andromeda's current asymmetry is a fossil wave from that ancient violence. Another clue is the ring of star formation that circles the galaxy at about 32,000 light-years from the center. In ultraviolet and infrared images, this ring stands out as a bright band studded with young star clusters and glowing gas clouds. Why should star formation be enhanced at that specific radius? One answer involves the central bar. Bars can funnel gas inward and outward, piling it up at particular orbital resonances, where the gravitational tug of the bar and the rotation of the disk sync in a special way. Where gas accumulates, it can cool and fragment, igniting new stars. The earlier merger likely helped establish and strengthen the bar, which in turn helped carve out the ring. It is a feedback loop on galactic scales. A collision disturbs the disk, the disturbance encourages a bar to grow, the bar reshapes the gas flow, and the gas responds by forming a ring of new stars. The result, billions of years later, is a galaxy whose spiral arms and star-forming sites still carry the imprint of a long-gone intruder. Within the arms, and especially along that ring, live the molecular clouds that fuel ongoing star formation. These are the coldest, densest parts of the interstellar medium, made mostly of molecular hydrogen with traces of carbon monoxide, ammonia, and other molecules. They can stretch for hundreds of light-years and contain enough raw material to build millions of stars. Seen in visible light, they often appear as dark lanes, silhouetted against the brighter backdrop of the disk. Switch to infrared, and they glow softly with the warmth of embedded young stars. As the density wave sweeps through, it compresses these clouds, pushing some regions over the threshold where gravity wins over internal pressure and turbulence. Inside, countless smaller cores collapse to form stars of all masses. Massive stars blaze and die quickly. Medium-mass stars like the Sun live for billions of years. Tiny red dwarfs sip fuel so slowly that they will still be shining when the universe is far older than it is today. All of those lives began because a wave of slightly higher density happened to pass through a cloud at the right time. The aftermath of the ancient merger adds another layer to this. Some of the gas in Andromeda did not settle smoothly into the disk. It arrived with strange orbits, misaligned with the main rotation. Over time, gravitational torques from the disk and bar have been trying to bring that gas into order. In the process, it can be shocked, compressed and cooled, triggering extra episodes of star formation in unusual places. The galaxy is still, in a sense, digesting that earlier meal. When you put all of this together, the pretty spiral you see in pictures stops being just a geometric pattern. It becomes a living record of processes stacked on processes. Density waves shaping where gas collapses. massive stars marking those zones with light and then seeding them with heavy elements when they explode. A bar, born and strengthened by past interactions, sculpting rings where stars form most intensely. And beneath it all, the long ghost of a collision that happened hundreds of millions of years ago, still echoing through the positions of arms and rings today. From your backyard, none of that complexity is apparent. You see a faint elongated patch if you are lucky, maybe a hint of structure through binoculars. Yet hidden inside that blur is a huge rotating system that remembers being struck and shaken. Its arms are not just decoration. They are the way gravity, gas and time write history into the shape of a galaxy. In the next part, we will zoom in on the clouds and shells that make that history visible, from glowing star-forming regions to the delicate remnants of dead suns, and see how Andromeda constantly recycles its material from one generation of stars to the next. If you could float inside Andromeda, you would discover that its disk is not just a smooth sea of stars. It's full of clouds, shells, bubbles, and knots of glowing gas. Some of these are stellar nurseries where new stars are being born. Others are the funeral shrouds of stars that have just died. Together they form the machinery that takes raw hydrogen, builds it into heavier elements inside stars, and then returns that enriched material back to the galaxy to start the process again. Andromeda is not just shining, it is constantly recycling itself. Let us begin with the most dramatic of these structures, the big glowing star-forming regions. Astronomers call them hydrogen-2 regions, or emission nebulae. They're immense clouds of gas where ultraviolet radiation from hot young stars strips electrons from hydrogen atoms. When those electrons recombine with protons, they emit light at very specific colours, especially a deep red known as hydrogen alpha. In long-exposure photographs, these regions show up as rich red and pink patches scattered along Andromeda's spiral arms and star-forming ring. Inside these hydrogen-2 regions, newborn clusters of massive blue stars are doing two things at once. On the one hand, their light is what makes the nebulae glow. On the other, their stellar winds and radiation are carving cavities and compressing nearby gas. That interplay can trigger further rounds of star formation in dense knots, while dispersing more diffuse gas elsewhere. When you look at one of these nebulae, you're seeing a feedback loop written in light, new stars sculpting and lighting the clouds that created them. Not all nebulae mark beginnings. Some are quiet announcements of an ending. Planetary nebulae are a perfect example. Despite the name, they have nothing to do with planets. The term stuck because in small early telescopes they looked like tiny disks. A planetary nebula forms when a medium-mass star, something broadly similar to the Sun, reaches the end of its red giant phase. Instabilities in its outer layers cause the star to pulsate and shed shells of gas into space. Eventually, the star exposes its hot core, now a white dwarf with a surface temperature that can exceed 100,000 degrees. Ultraviolet light from this exposed core ionizes the expanding shells around it, making them glow in delicate blues and greens. In Andromeda, thousands of such planetary nebulae are scattered through the disk and bulge, each only visible for a relatively brief time, maybe tens of thousands of years, before the gas fades into the background. Every one of them marks a star that has finished its main sequence life and is quietly retiring as a white dwarf. Then there are endings that are anything but quiet. When a massive star dies, it does not gently shrug off its outer layers. It explodes as a supernova. For a few weeks, a single star can outshine an entire galaxy. The blast hurls the star's outer material into space at tens of thousands of kilometers per second. The ejector plows into surrounding gas, creating a shockwave that heats the material to millions of degrees. The result is a supernova remnant, an expanding bubble or shell that glows in X-rays and visible light. In Andromeda, astronomers have identified dozens of supernova remnants, especially in X-ray observations that cut through the clutter of normal starlight. The youngest and brightest still show clear shell structures. Others have grown larger and fainter, gradually blending into the general interstellar medium over hundreds of thousands of years. Each remnant is more than just a pretty filament. It is the main way massive stars return their processed material to the galaxy. Inside those exploding stars, elements heavier than helium were forged through nuclear fusion and, in the final seconds, through a rapid capture of particles during the explosion itself. Oxygen for future oceans, silicon for rocks, iron for cores and for your blood, carbon for organic chemistry. All of these elements are blown outward and mixed into the surrounding gas. When new stars and planets form later from that enriched material, they carry the fingerprints of earlier generations of massive stars. Some nebulae do not glow on their own at all. Reflection nebulae are clouds of dust that simply scatter starlight. They tend to appear blue in images because blue light scatters more efficiently than red. The same basic physics that makes Earth's sky blue. You often find them near young star clusters, where dust has not yet been fully cleared out. In Andromeda's star-forming regions, reflection nebulae wrap some clusters in soft blue halos, revealing where dust is still thick enough to reflect light, but not dense enough to block it entirely. On the opposite end of the spectrum, dark nebulae are clouds so dense and dusty that they block light altogether. Against the bright background of a star-rich disk or an emission nebula, they appear as sharp black shapes, like holes torn in the sky. In visible light images of Andromeda, dark lanes trace through the spiral arms, especially on the side of the disk that tilts toward us. These lanes are the silhouettes of cold molecular clouds packed with gas and dust. Inside those dark clouds, gravity is quietly doing its work. Shielded from harsh radiation by surrounding dust, gas can cool to very low temperatures. Small fluctuations in density grow over time, eventually forming the dense cores that will collapse into new stars. In that sense, every dark nebula is a promise. What looks like absence of light is actually the hiding place of future suns and perhaps future planets. When you step back and look at all these structures together, a pattern emerges. Hydrogen-2 regions and reflection nebulae highlight the places where stars have just been born. Planetary nebulae and supernova remnants highlight the places where stars have just died. Dark nebulae and molecular clouds mark the reservoirs of raw material. The galaxy uses stars as engines to transform simple gas into complex elements, then uses stellar deaths to throw those elements back into space, ready to be built into new stars and planets. Andromeda is large enough and old enough that all stages of this cycle are happening at once across its disk. Somewhere in one spiral arm, a massive star might be collapsing and detonating right now in Andromeda's present, seeding a region with heavy elements. Elsewhere, a new cluster is emerging from its natal cloud, pushing away the last of its gas. Farther out, a quiet planetary nebula is fading as its central white dwarf cools. The galaxy looks static on human timescales, but inside its nebulae, the story of birth, life and death plays continuously. From Earth, we cannot see most of these details with our own eyes. We rely on telescopes tuned to different wavelengths to trace glowing gas, hot X-ray shells and cold dust. But conceptually, you can fold all of that back into the simple fuzzy patch you find in the Andromeda constellation. That blur is not just stars. It is a factory where matter itself is being cycled from clouds to stars to nebulae and back again over and over for billions of years. In the next part, we will leave the individual clouds behind and step out to the full architecture of the galaxy, from its thin rotating disk to its vast halo studded with globular clusters, and then meet the invisible dark matter that supplies most of its gravity. So far we have been wandering inside Andromeda's bright neighbourhoods, moving from spiral arms to star-forming clouds to the ashes of dead suns. Now it is time to step back and look at the way all of that is arranged on the grandest scales. A galaxy is not just a pretty picture, it is an architecture, a way that gravity, rotation and invisible matter fit together. Andromeda's structure falls into three main visible pieces: the thin disk where most of the stars live, the vast faint halo that surrounds it, and the dense swarms of globular clusters that orbit in between. Lurking underneath all of that is something we cannot see at all, the dark skeleton of matter that supplies most of the galaxy's gravity. Start with the disk, because that is the part we recognize from photographs. It is a flattened, rotating slab of stars, gas and dust, about 220,000 light-years across, but only around 1,000 light-years thick in its main star-filled layer. That proportion make it more like a cosmic pancake than a ball. The disk is where you find Andromeda's spiral arms, its bar, its star-forming ring, and a huge fraction of its total starlight. Most of the stars that look familiar to us, sun-like stars and small red dwarfs, live in this region, orbiting the centre in nearly circular paths. The disk did not become flat by accident. When the galaxy was young, gas and stars moved in all directions, but as gas clouds collided, they could radiate away energy and settle. The one thing they could not lose easily was their net angular momentum, their overall spin. The easiest configuration for a large spinning system is a rotating disk perpendicular to the spin axis. It is the same reason spinning pizza dough flattens out. Random up and down motions get damped over time, while rotation around a central axis remains. That disk is not perfectly thin or uniform. Closer to the center, the gravitational pull is stronger and the density of stars higher, thickening the inner regions. Over billions of years, encounters with giant molecular clouds and passing satellite galaxies have stirred the disk, puffing up older stellar populations so that they live in a thicker layer above and below the main plane. Young stars tend to hug the thin midplane, while older stars occupy a thicker, more diffuse component. Seen edge-on, Andromeda would show a bright thin streak with a softer envelope around it, the visible sign of its long dynamical history. Beyond the disk lies a very different kind of structure, the stellar halo. If the disk is the city, the halo's the sparse countryside that stretches out far beyond the last streetlights. Andromeda's halo extends to at least 500,000 light-years from the center, more than twice the radius of the bright disk. Yet it contains only about 1% of the galaxy's stars. That means the average distance between halo stars can be hundreds of light-years. If the sun lived out there, the nearest star might be so far away that the night sky would be almost empty, a dark dome with a brilliant central galaxy dominating one area and little else. The stars in this halo are mostly ancient, metal-poor population 2 stars, relics from early in the galaxy's life. Many did not form in Andromeda at all. They were born in smaller dwarf galaxies that later wandered too close and were torn apart. As those satellites were shredded by tidal forces, their stars were stretched into long streams that wrap around Andromeda in complex loops. Over time, those streams disperse and blur, but they never vanish entirely. Deep imaging surveys have revealed dozens of them, faint rivers and shells of stars that crisscross the outer halo. Each one preserves a chapter of Andromeda's merger history. Among these halo stars live some of the most spectacular objects in any galaxy, the globular clusters. Andromeda hosts roughly 450 of these, possibly more. A globular cluster is not a loose association of stars. It is a compact, gravitationally bound sphere containing hundreds of thousands or even millions of stars crammed into a region only tens or hundreds of light-years across. The stars inside are old, often more than 12 billion years in age, and very metal-poor. In a sense, they are little fossil galaxies, survivors from the earliest stages of structure formation. One of the most massive clusters in Andromeda is known as G1, or sometimes Mayol 2. It contains several million stars and is so bright that it was once mistaken for a small galaxy. Observations suggest that G1 may even harbour an intermediate mass black hole in its core. If you could stand on a planet orbiting a star in the centre of such a cluster, your night sky would be crowded almost beyond imagination. Thousands of stars would rival or outshine Venus as seen from Earth. True darkness would never fall. These globular cities orbit Andromeda on elongated paths that can carry them far into the halo and then plunge them back through the disk. Each passage through the crowded inner regions exposes them to tidal forces and encounters with gas clouds that can strip away their outer stars. Over billions of years, some clusters are whittled down, leaving faint, dissolving remnants. Others, on safer orbits, remain largely intact. Together, they form a kind of fossil record, telling us about the conditions in the early universe when they formed, and about the gravitational landscape they have moved through ever since. Even when you add up the mass of the disk, the bulb, the halo stars, the gas, the dust, and all those globular clusters, something does not add up. The way Andromeda rotates refuses to match the gravity that its visible matter should provide. When astronomers measure how fast stars and gas orbit at different distances from the center, they find that beyond the inner regions, the orbital speed stays roughly constant instead of declining. If only the visible mass were present, the outer stars should move more slowly, the way planets in the outer solar system orbit more slowly than those close in. Instead, the outer parts of Andromeda are whipping around faster than they should be able to without flying away. This mismatch is encoded in what is called the rotation curve. Plot orbital speed versus distance from the center, and instead of a curve that rises and then falls, you get a curve that rises and then flattens out. The simplest way to explain this is to admit that there must be more mass than we can see, distributed in a large extended halo around the galaxy. That unseen mass is what we call dark matter. It does not emit light, does not absorb it, does not scatter it. It only reveals itself through gravity. In Andromeda, as in most galaxies, dark matter dominates the mass budget. For every kilogram of normal matter, there are roughly several kilograms of dark matter. The dark halo is roughly spherical and extends far beyond the visible stellar halo, perhaps out to 600,000 light-years or more. The bright disk and bulge that we see are like the luminous core of an iceberg, floating in a much larger invisible sea. Without that dark skeleton, the galaxy could not hold itself together at the observed rotation speeds. The disk would slowly unravel, stars drifting away into intergalactic space. We do not yet know what dark matter is made of. It is unlikely to consist of ordinary atoms because measurements of the early universe's light element abundances and the cosmic microwave background suggest there simply is not enough normal matter to account for its effects. Physicists have proposed exotic particles with weak interactions. Experiments deep underground and in particle accelerators are searching for them. So far, all we have is the gravitational fingerprint. Andromeda's flat rotation curve and massive halo are part of that fingerprint. When you put everything together, a new picture emerges. The thin, bright disk where stars form and die is only one layer. Above and below it stretches a vast halo of ancient stars and stellar streams, dotted with dense globular clusters that act as fossil clues. Around and through all of that lies an even larger, completely invisible halo of dark matter that defines the overall gravitational well. Andromeda's graceful spiral is not just a pattern of light. It is the visible skin of a much deeper structure, shaped by forces we partly understand and by matter we can only infer. In the next part, we will turn from structure to measurement. How do we actually know Andromeda is as far away as we say? And how did one fuzzy patch in the sky help us build a ladder that reaches to the edge of the observable universe? Up to now, we have treated the distance to Andromeda as something already known, as if someone simply looked it up in a cosmic address book. But every number in astronomy is paid for with ingenuity. You cannot fly there with a tape measure. You cannot bounce a laser off it and wait for the echo. So how do we know that this faint oval in the sky is 2.54 million light-years away, and not 200,000 or 20 million? In this part, we're going to climb the cosmic distance ladder, rung by rung, and see why Andromeda is one of the most important steps on it. The ladder begins close to home where we can do something simple and direct. In our own solar system, we can measure distances with radar, send a burst of radio waves toward the moon, wait for the echo, and time how long it takes to return. Since radio waves travel at the speed of light, that round-trip time gives a distance. Do the same trick with nearby planets, and you can map out the architecture of the inner solar system in kilometers and miles. From there, you define a basic unit, the astronomical unit. The average distance from Earth to the Sun is about 150 million kilometers, roughly 93 million miles. Once you know that unit, you can use geometry to reach farther. As Earth orbits the Sun, nearby stars appear to shift slightly against the background of more distant stars. This apparent wobble is called parallax. Hold out your thumb and blink one eye, then the other, and you see the same effect. Your thumb jumps back and forth against the distant wall because you are viewing it from two positions. Replace your head with the Earth's orbit and your thumb with a nearby star, and you have the basic idea. Measure that tiny shift over 6 months when Earth has moved to the opposite side of its orbit, and with some trigonometry you can work out the star's distance. For the closest stars, that parallax angle is still tiny, often measured in thousandths of an arcsecond. Space missions like Hipparcos and later Gaia have measured parallaxes for more than 1 billion stars in our galaxy. This gives us solid distances out to a few thousand light-years, enough to calibrate the next rung of the ladder. Beyond that range, parallax becomes too small to measure accurately. The wobble disappears into the noise. To keep going, astronomers had to find objects whose true brightness is knowable without knowing their distance first. These are called standard candles. The idea is simple. If you know how bright a certain kind of object really is, and you can measure how bright it looks from Earth, you can work out how far away it must be. It is like recognizing that a light on a distant hill is a 100-watt bulb. The dimmer it looks, the farther away it must be. One of the most important standard candles in the universe is a special class of variable star called a Cepheid. These are massive pulsating stars whose brightness rises and falls in a regular rhythm. The key discovery came from Henrietta Swan Leavitt in the early 1900s. Studying Cepheids in nearby star clusters she realised that the longer a Cepheids' pulsation period, the more luminous it actually is. In other words, period and true brightness are linked. Measure the period and you can infer the luminosity. Once that relation is calibrated using stars whose distances we already know from parallax, Cepheids become distance markers. Edwin Hubble used this method in the 1920s with the 100-inch telescope at Mount Wilson. He pointed it at Andromeda's fuzzy patch and for the first time resolved individual stars. Among them, he identified Cepheid variables. By tracking their periods and apparent brightnesses, he could estimate how far away they were. Hubble's initial calculation put Andromeda at roughly 900,000 light-years. That was an underestimate, partly because astronomers did not yet realise there are two main types of Cepheids with slightly different period luminosity relations, but the exact number was less important than the conclusion. Whatever the precise distance, Andromeda was far outside the Milky Way. It was not a small cloud within our own stellar system. It was an entirely separate galaxy, an island universe in its own right. That single step shattered the old picture of a universe containing only our galaxy and expanded our sense of scale by orders of magnitude. Modern work has refined Hubble's rough distance enormously. Space telescopes can measure Cepheid variables in Andromeda far more accurately than ground-based observatories ever could. With better calibrations and better understanding of stellar physics, the distance now stands at about 2.54 million light-years. With an uncertainty of only a few percent, that may sound like a small change, but tightening that value matters, because Andromeda is not just any galaxy. It is a key anchor for the rest of the distance ladder. Beyond galaxies like Andromeda, even Cepheids become too faint and too rare to use easily. To reach across hundreds of millions or billions of light-years, astronomers rely on even brighter standard candles, especially a kind of exploding star known as a Type I supernova. These events occur when a white dwarf in a binary system steals enough material from its companion to reach a critical mass. The star then undergoes a runaway thermonuclear explosion, destroying itself in a flash that briefly rivals the brightness of an entire galaxy. The helpful part is that Type I supernovae reach nearly the same peak luminosity each time, once you account for a few known variations. That makes them excellent beacons, but to use them as distance markers, you must first calibrate their true brightness in nearby galaxies where you already know the distance from Cepheids. Andromeda sits right in that sweet spot. It is close enough that we can measure Cepheid distances accurately, but far enough away that in principle, Type I supernovae, they would resemble those in more distant galaxies we want to study. This chain from radar to parallax to Cepheids to supernovae is what astronomers call the cosmic distance ladder. Each rung rests on the one below it. Each measurement depends on the accuracy of the earlier ones. When you read that the universe's expansion is accelerating, or that a distant galaxy is billions of light-years away, buried inside those statements is the fact that we trust our calibration of systems like Andromeda. The discovery of the accelerating universe in the late 1990s came from observing Type I supernovae in very distant galaxies and comparing their brightness with expectations. Those expectations, those model distances, trace back through supernova calibrations to Cepheids, and then down the ladder all the way to the careful radar pings and parallax measurements in our own neighbourhood. Andromeda is one of the main bridges between the part of the universe we can measure directly and the part we can only infer. So when you hear that Andromeda is 2.54 million light-years away, you are hearing more than a distance. You are hearing the outcome of a century of work, from Henrietta Leavitt's painstaking study of flickering stars to Hubble's first Cepheids in that fuzzy patch, to modern space telescopes refining those measurements so tightly that they can support cosmology. A galaxy you can never visit has become a carefully measured landmark, a fixed point in our mental map of the universe. In the next part, we will move from measuring distances to understanding what lives at those distances. We will follow the lives and deaths of stars inside Andromeda and see how their individual stories combine to shape the galaxy's light, its chemistry, and its future. If you could somehow mute all of Andromeda's gas and dust and nebulae and see only its stars, you would still be looking at a wildly diverse crowd. Some are tenae, faint embers that will outlive the universe. Some are swollen red giants near the end of their lives. Others are massive blue furnaces burning so fiercely that they will be gone almost as soon as they appear. The story of Andromeda is really the story of these stars and how they live die, and change the galaxy's chemistry over billions of years. Every star begins the same way. Deep inside a cold molecular cloud, gravity wins a slow argument against pressure and turbulence. A clump of gas collapses, heats up, and forms a proto-star surrounded by a rotating disk. When the core temperature reaches around 10 million degrees, hydrogen nuclei begin to fuse into helium. At that moment, the star turns on. Outward pressure from fusion balances gravity pulling inward, and the star settles into the long, stable middle part of its life called the main sequence. What happens next depends almost entirely on one number, the star's mass at birth. At the small end of the scale are red dwarfs. These stars have less than about 40% of the Sun's mass. They burn their hydrogen fuel slowly and efficiently, staying cool and dim compared to stars like ours. Their lifetimes stretch into the trillions of years, longer than the universe has existed so far. That means every red dwarf that has ever formed in Andromeda is still shining today. They are by far the most common kind of star in the galaxy, but because each one is faint, they contribute only a modest fraction of the total light. In visible images of Andromeda, you are mostly seeing the minority of stars that are bright enough to stand out. The vast red dwarf population is the invisible backbone of the stellar census. Stars with masses similar to the Sun live a different kind of life. They burn hotter and brighter and run through their core hydrogen more quickly. The Sun has been shining for about 4.5 billion years and will continue fusing hydrogen in its core for roughly another 5 billion. Many stars in Andromeda are in that same main sequence phase, quietly turning hydrogen into helium in their cores, their luminosity slowly creeping upward over time. When a sun-like star exhausts the hydrogen in its core, the balance it has enjoyed for billions of years breaks. The core contracts and heats, while hydrogen fusion continues in a shell around it. The outer layers respond by expanding and cooling. The star swells into a red giant, its radius increasing by tens or even hundreds of times. In Andromeda's bulge, countless such red giants glow with a reddish hue, giving the central region its warm colour. Some of these giants are so large that, if placed where our Sun is, they would engulf the orbits of Mercury and Venus and perhaps even Earth. Eventually, the core of a medium-mass star becomes hot and dense enough to ignite helium fusion, then heavier elements up to carbon and oxygen, but it never gets hot enough to fuse those elements further. The outer layers become unstable, pulsing and shedding gas into space. Over time, the star loses much of its envelope, exposing the hot core. That core becomes a white dwarf, an Earth-sized stellar ember packed with roughly the Sun's mass. It will cool slowly over trillions of years. The gas the star cast off drifts away, enriched with elements that will someday be part of new stars and planets. At the top of the mass scale live the giants that really put their stamp on Andromeda. Stars more than about 8 times the Sun's mass burn through their fuel wildly. A 20 solar mass star may live only a few million years. It spends that short life pumping out intense radiation and powerful winds that shape its surroundings. Inside its core, fusion proceeds not just from hydrogen to helium, but onward to carbon, oxygen, neon, silicon, and eventually iron. Each new fuel is used up faster than the last. The final stages of burning can last only thousands or even mere days. When the core fills with iron, the star is in trouble. Fusing iron does not release energy, it consumes it. Once the core grows too massive, it cannot support itself against gravity. In a fraction of a second it collapses. The outer layers fall inward, rebound off the suddenly stiffening core, and an enormous shock wave races outward. With help from neutrinos flooding out of the core, the star tears itself apart in a supernova explosion. For a brief time, the star can outshine the whole galaxy, then fades, leaving behind either a neutron star or a black hole. Andromeda probably experiences a few of these core collapse supernovae every century. We have not seen most of them because they explode between our watchful eras, but their remnants are there in X-ray maps and radio images, expanding bubbles of hot gas marking where massive stars ended their lives. Each supernova is a chemical factory going off. Heavy elements forged in the core are blasted into space and mixed into the interstellar medium. There is another class of supernova that plays an outsized role in both Andromeda's chemistry and our ability to study the universe. Many stars form in binary systems. In some of these pairs, one star evolves faster, becomes a white dwarf, and later starts pulling gas from its still-living companion. If the white dwarf accumulates enough material to push it near a critical mass, conditions in its interior can trigger runaway nuclear fusion. The entire star detonates in a thermonuclear supernova, completely unbinding itself. These are the so-called Type 1 events that astronomers use as standard candles. They also release large amounts of iron and other elements, enriching the galaxy in ways different from massive star explosions. Through all of this, the overall chemical makeup of Andromeda changes. The first generations of stars formed from nearly pristine gas, mostly hydrogen and helium left over from the Big Bang. When those stars died, they returned some of that material enriched with heavier elements. New stars formed from that slightly dirtier gas, lived and died, enriching it further. Today, typical young stars in Andromeda contain a few percent by mass of elements heavier than helium, similar to the Sun. That small fraction is everything solid in planets and everything complex in life. You can see this chemical evolution written across the galaxy. The bulge and halo, which host older populations, are dominated by the metal-poor stars. Their spectra show fewer heavy element lines. The disk, especially the spiral arms and star-forming ring, contains more metal-rich stars and gas. There, multiple generations of star birth and death have had time to build up heavier elements. Astronomers read these patterns as a kind of archaeological record. Stars of different ages and compositions act like core samples drilled through time. This ongoing enrichment has a direct implication for worlds and life. Rocky planets need heavy elements to exist. Carbon, oxygen, silicon, iron, phosphorus all must be present in sufficient quantities for Earth-like planets to form. Early in the universe, galaxies like Andromeda would have been poor in those elements, making rocky planets rare or impossible. As billions of years passed and supernovae and stellar winds returned more and more metals to the gas, the odds of forming planets with solid surfaces, atmospheres, and perhaps oceans increased. In that sense, Andromeda has been slowly changing from a place where complex worlds were unlikely into a place where they may be common. When you look at the faint smudge of Andromeda and imagine its trillion stars, you are really looking at a vast ensemble of living, evolving engines. Tiny red dwarfs that will shine for longer than galaxies themselves. Sun-like stars midway through their calm lives. Red giants swelling as they approach the end. Massive blue giants rushing towards spectacular deaths. White dwarfs cooling in silence. Neutron stars and stellar mass black holes left behind as compact ghosts. Each star is a step in the galaxy's long chemical story, turning simple gas into the ingredients for planets and possibly life. In the next part, we will turn our attention to forces you cannot see directly in optical images at all. The magnetic fields and high-energy particles that thread Andromeda and quietly influence everything from star formation to radio emission. By now you might feel you have a pretty good mental picture of Andromeda. A bright disk, spiral arms, star-forming clouds, a big bulge, a dark matter halo. But there is another layer to this galaxy that you never see in ordinary images. Andromeda is threaded with magnetic fields and filled with high-energy particles racing around at close to the speed of light. These invisible ingredients help shape how gas moves, where stars form, and how the galaxy glows in radio and high-energy light. To understand the true Andromeda, we have to learn to see its invisible weather. Magnetic fields in galaxies are not simple bar magnets floating in space. They are generated and maintained by a movement of ionized gas, a process called a dynamo. Imagine electrically conducting gas orbiting the galaxy, shearing, stirring, and twisting. Those motions take tiny seed fields and amplify them over time. The result in a galaxy like Andromeda is a large-scale magnetic field that roughly follows the spiral arms, with strengths of only a few millionths of the strength of Earth's field, but spread over hundreds of thousands of light years. That might sound too feeble to matter. Yet across galactic scales, even such weak fields have serious influence. They thread through gas clouds, exerting pressure and tension. They guide the motion of charged particles, forcing them to spiral along field lines rather than moving freely. They provide a kind of magnetic scaffolding that supports part of the weight of the interstellar medium against gravity. If you could somehow flip Andromeda's magnetic field off, the way you might kill the power to a city grid, gas clouds would collapse and move differently. Star formation rates and patterns would change. The clearest way we know these fields exist is through radio waves. High-energy charged particles, mostly protons and electrons, zip through Andromeda's magnetic field at nearly the speed of light. As they spiral along field lines, they emit a special kind of radiation called synchrotron emission. This shows up as smooth radio glow that traces the spiral arms and extends into the halo. When we map that radio light and measure how it is polarized, we can infer the strength and geometry of the magnetic field that shaped it. Those fast-moving particles are cosmic rays, and they deserve their own attention. A cosmic ray is not a ray at all, but an individual particle, often a proton or an atomic nucleus, accelerated to enormous energies. Many of them are born in supernova remnants. As the shock wave from a stellar explosion plows into surrounding gas, it can bounce charged particles back and forth across the shock front, giving them little kicks each time. After enough kicks, some particles escape at relativistic speeds. These become part of the cosmic ray population that fills Andromeda. Cosmic rays do not move in straight lines for long. Magnetic fields bend their paths, causing them to wander in tangled spirals through the disk and halo. This confinement means they stick around, bumping into gas atoms, ionizing them, and heating them. In places where cosmic rays are dense, they contribute pressure to the interstellar medium comparable to that of thermal gas or starlight. When you think of what holds up gas clouds against gravity, you have to count not just temperature and turbulence, but also the push from these invisible high-energy particles. When cosmic rays collide with gas, interesting things happen. High-energy collisions can produce gamma rays and lighter particles. Satellites that detect gamma rays see Andromeda as a faint but real source, a sign that cosmic rays are slamming into its gas. Radio telescopes see the synchrotron glow from electrons spiraling through the magnetic field. Together, these signals let astronomers map where cosmic rays are most abundant and how they relate to regions of star formation and supernova activity. Magnetic fields also interact with star formation in more subtle ways. In a cold molecular cloud, gas is mostly neutral, but a small fraction is ionized and tied to the field. As gravity tries to pull the cloud together, the field resists, providing extra support. For collapse to proceed, neutral gas must gradually slip past the ionized component in a process called ambipolar diffusion. That slow drift lets some parts of the cloud shed magnetic support and collapse into stars while other parts remain held up. In this way, magnetic fields act as regulators, helping set the pace at which a galaxy like Andromeda turns gas into new suns. The influence of magnetism is not limited to the disk. Andromeda's halo also hosts magnetic fields, though weaker and more tangled. These may be generated by outflows of gas driven by supernova explosions and stellar winds in the disk. Hot gas, enriched with heavy elements and cosmic rays, can flow out along field lines into the halo, creating a kind of fountain. There the gas may cool and eventually rain back down. This circulation connects the star-forming disk with the hot, thin, extended halo, distributing energy and metals across large distances. From Earth's perspective, all of this is utterly invisible to the naked eye. If you look at Andromeda in optical light only, you miss the magnetic skeleton and the high-energy particle storm. But when you overlay radio maps that trace synchrotron emission, gamma-ray maps that reveal cosmic ray collisions, and X-ray maps that show million-degree gas, the galaxy looks very different. It becomes not just a serene spiral, but a dynamic, energized system where explosions, fields, and fast particles are constantly exchanging energy with gas and dust. The reason this matters is that galaxies are not just piles of stars sitting in gravitational wells, they are ecosystems. Magnetic fields shape how gas flows. Cosmic rays heat and ionize that gas. Together with radiation and gravity, they help determine where stars can form, how long gas clouds survive, and how energy from dying stars spreads through the galaxy. Andromeda's current appearance, from its spiral arms to its faint radio halo, is the visible result of this ongoing invisible weather. In the next part, we will shift from forces and fields back to our instruments. We will tour Andromeda across the electromagnetic spectrum from radio waves to gamma rays and see how each kind of light reveals a different layer of this galaxy's story. When you look at Andromeda with your eyes, you are using one tiny window in a much larger spectrum. Human vision is tuned to a narrow band of wavelengths that happen to slip through Earth's atmosphere and work well for day-to-day life on a planet. The galaxy does not care about those limits. It shines, absorbs, and glows across a huge range of energies from long, lazy radio waves to furious gamma rays. In this part, we are going to slide a cosmic filter wheel in front of Andromeda and watch how the galaxy changes every time we switch to a different kind of light. First, picture the electromagnetic spectrum as a stretched string. At one end are radio waves with long wavelengths longer than a house, even longer than a city. Move along the string and the waves get shorter and more energetic. Microwaves, then infrared, then the visible band our eyes use, then ultraviolet, then X-rays, and finally gamma rays with wavelengths smaller than atomic nuclei. It is all the same phenomenon, just different energies. Andromeda radiates in all of them, but each band tells a different story. Start at the long wave end with radio. In radio light, stars fade into the background. What jumps out instead is gas, magnetic fields, and cosmic rays. One of the most important radio signals is the 21 centimeter line from neutral hydrogen. Each hydrogen atom can flip the orientation of its proton and electron spins, releasing a photon at that specific wavelength. It is a tiny effect, but when you have clouds containing billions of atoms, the combined signal is strong enough to map. Radio telescopes tuned to this line trace the distribution of cold atomic gas in Andromeda. The maps show a disk that extends far beyond the visible stars, and that disk is warped and lopsided. One side sticks out farther, and the outer regions tilt relative to the inner disk. These warps and twists are the signatures of past interactions, echoes of encounters with other galaxies and streams of gas. Radio observations also reveal high-velocity clouds that do not follow the normal rotation pattern, hints of ongoing accretion and disturbance in the halo. On top of the hydrogen line sits a smoother radio glow. That is synchrotron emission from cosmic ray electrons spiraling through Andromeda's magnetic field. It outlines the spiral arms and extends into the halo, tracing where magnetic fields are strongest and where recent star formation and supernova activity have pumped high-energy particles into space. In radio, Andromeda looks less like a tidy spiral and more like a glowing, magnetized weather system. Shift the dial to slightly shorter wavelengths and you reach microwaves. Here you are mostly seeing cold dust, grains only a few tens of degrees above absolute zero. Telescopes sensitive to microwaves detect this faint thermal glow. The result is a map of the coldest material in Andromeda, the stuff still locked up in molecular clouds and outer disk structures. Where optical images show only darkness, microwave images reveal reservoirs of dust and gas waiting to become future stars. Slide further along into the infrared and things warm up. Dust grains heated by nearby stars to temperatures of a few tens or hundreds of degrees above absolute zero radiate strongly in infrared light. Space telescopes like Spitzer have used this to produce stunning images of Andromeda, where the spiral arms blaze as bright lanes of warm dust. Those lanes mark active or recent star formation. Young stars, especially massive ones, pour out radiation that heats surrounding dust and makes it shine in the infrared long after the most massive stars themselves have exploded. Infrared light also pierces through much of the dust that blocks visible light. That lets us see older, cooler stars that are hidden in optical images. In the central bulge, infrared observations reveal the true structure and density of red giant populations. In the disk, they show a smoother backdrop of older stars behind the patchy dust lanes. Combine that with radio maps of gas, and you get a picture of both the fuel and the leftovers of star formation. Now switch to the band your eyes actually use, visible light. This is the radiation from the photospheres of stars, the surfaces from which their light escapes. In visible images, Andromeda looks like the classic spiral. Blue tinges trace young stars in the arms. Yellow and red tones fill the bulge and older disk. By imaging in several colours and measuring how bright the galaxy is in each, astronomers can estimate stellar temperatures, ages, and compositions. The pattern of colours reveals where stars are young, where they are old, and how star formation has proceeded over time. Step just beyond the violet end and you arrive in ultraviolet. Here only the hottest stars dominate. Massive O and B type stars with surface temperatures well above 10,000 degrees emit most of their light in ultraviolet wavelengths. A galaxy-wide ultraviolet map of Andromeda lights up the active star-forming ring and the spiral arms with intense patches. Regions that look modest in visible light can burst into prominence in ultraviolet because a handful of very hot young stars overwhelm thousands of cooler ones. Instruments like the Galaxy Evolution Explorer have used this contrast to catalogue thousands of star-forming regions and young clusters scattered through the disk. Keep turning the knob to higher energy and you reach X-rays. This is the realm of gas heated to millions of degrees and of compact, extreme objects. X-ray telescopes like Chandra see Andromeda as a galaxy speckled with hotspots. Supernova remnants shine as extended blobs where shockwaves have heated gas. Binary systems where a neutron star or stellar mass black hole is feeding on a companion star flare as bright points. Gas falling onto these dense objects releases gravitational energy as it spirals in, and that energy is radiated as X-rays. Even the supermassive black hole at Andromeda's center shows up occasionally in X-ray light when it snags a gas cloud or star. Most of the time it is quiet, a faint source compared to the population of X-ray binaries. Surrounding all of this, a faint X-ray halo reveals very hot diffuse gas in the outer regions, heated by the combined action of supernovae and galactic outflows. In X-rays, Andromeda is not a calm spiral but a battlefield of explosions, accretion, and million-degree plasma. Push to the shortest wavelengths and highest energies and you hit gamma rays. These photons carry the most energy of any kind of light. They are produced when cosmic rays collide with gas, when certain radioactive isotopes created in supernovae decay, and in the most extreme environments around neutron stars and black holes. Gamma ray telescopes see Andromeda as a very faint compact source, but it is there. That detection tells us that high-energy particle interactions are happening throughout the galaxy, even if we cannot resolve individual sources. No single one of these views gives you the whole Andromeda. Visible light maps the stars. Infrared reveals dust and hidden stellar populations. Radio and microwaves show gas, magnetic fields, and cosmic rays. Ultraviolet highlights the hottest newborn stars. X-rays and gamma rays expose violent deaths and extreme physics. The real power comes when you stack these maps on top of each other. Do that and the galaxy turns into a layered object. Spiral arms that look smooth in visible light break apart into dust lanes, star-forming knots and hot bubbles. The quiet bulge reveals a crowded core in infrared, and sporadic high-energy flares in X-rays. The outer disk, faint to the eye, stretches far in hydrogen and dust. The radio halo extends beyond the optical edge, tied to magnetic fields and cosmic rays. In effect, each wavelength is a different sense. Our eyes give us one impression, but to understand Andromeda as it really is, we need radio ears, infrared skin, ultraviolet goggles, and X-ray vision. Telescopes become prosthetic senses that let a primate brain, evolved on one small planet, perceive a galaxy in all its complexity. In the next part, we will leave the spectrum of light and return to the force that holds all of this together. We will look at how gravity shapes Andromeda's orbits, keeps the disk still, and choreographs the slow interactions with its satellites and with the Milky Way itself. Everything we have talked about so far, from spiral arms to star-forming rings to hot gas halos, is ultimately controlled by one quiet thing: gravity. No matter how many layers you peel back, you keep finding the same rule underneath. Mass attracts mass. Andromeda is what happens when that simple rule operates on a truly ridiculous scale for billions of years. In this part, we are going to step into the role of a cosmic traffic engineer and look at how gravity sets up orbits, keeps the disk from collapsing, and choreographs the long, slow interactions between Andromeda, its satellites, and even the Milky Way. Imagine the entire galaxy sitting in an invisible bowl, a gravitational valley carved mostly by its dark matter halo and filled in by its stars and gas. This bowl is what physicists call the gravitational potential. Objects near the bottom feel a strong pull and move quickly. Objects out near the rim feel a weaker pull and move more slowly, but as long as they do not get a big extra kick, they remain trapped in the valley. That is what it means for Andromeda to be a gravitationally bound system. Every star, every gas cloud, every globular cluster is sliding around in this same invisible contour. Inside that big valley, the disk is kept up by rotation. If there were no motion at all, gravity would simply pull everything straight inward, and Andromeda would collapse into a dense ball in a few 100 million years. Instead, stars and gas orbit the center at hundreds of kilometers per second. That orbital motion produces an outward centrifugal tendency that balances gravity. In the inner regions, the balance is like a tight, fast racetrack. Closer to the edge of the disk, the track is wider and the laps take hundreds of millions of years to complete. These orbits are not simple circles copied and pasted from a textbook. The gravitational field of a real galaxy is not perfectly symmetrical. The bar in the center, the spiral arms, lumps of dark matter, and passing satellites all add little bumps and dimples to the potential. As a result, many stellar orbits take on rosette shapes rather than closed ellipses. Over time, those rosettes precess, slowly rotating their orientation. Some stars follow paths that carry them above and below the plane of the disk before bringing them back through it. Others glide in nearly flat circular tracks for billions of years with only gentle perturbations. When stars move through the disk, they occasionally pass near giant molecular clouds, those massive cold structures that can contain millions of solar masses of gas. Even though the stars and clouds are widely separated in absolute terms, a close passage by one of these heavyweights can give a star a noticeable gravitational tug. It is a bit like driving down a highway and feeling your car drift when you pass a huge truck. Each individual interaction is small, but over billions of years, millions of such encounters gradually kick stars onto slightly more tilted and eccentric orbits. This process slowly thickens the disk, making older stellar populations puffier than younger ones. There is an even slower kind of stirring called relaxation. Every star in the disk feels tiny gravitational nudges from every other star. Each nudge is minuscule, but they do not cancel perfectly. Over timescales longer than the age of the universe, this background chatter of gravity would completely randomize orbits. In practice, other processes dominate before that happens in a spiral galaxy, but the idea is important. Nothing in the galaxy is perfectly static. The disk slowly heats and thickens as stars trade a little orbital energy and angular momentum back and forth. Spiral arms and bars are also products of gravity. In earlier parts, we talked about spiral arms as density waves. Those waves do not just appear out of nowhere. They grow from small disturbances in the disk that get amplified by the galaxy's own gravity and differential rotation. A patch of disk that is slightly denser than average pulls more strongly on its surroundings, drawing in more material and enhancing the pattern. Under the right conditions, those amplified ripples line up into long, trailing spirals. The whole process is known as swing amplification, and it explains why spiral patterns are so common in rotating disks. Bars form through similar instabilities. If the inner disk has enough self-gravity and moves in the right way, elongated orbits can align and reinforce each other, producing a bar-shaped structure that rotates as a unit. Once a bar forms, it changes the gravitational landscape. It channels gas along its length, can drive material inward toward the center, and sets up resonances where gas piles up and star formation intensifies. In Andromeda, that is likely connected to the bright ring of star formation we see at a specific radius. A bar is gravity's way of rearranging angular momentum inside a disk. Now zoom out past the edges of the bright disk. Out there, small companion galaxies move through the same dark matter halo. Andromeda has at least a dozen known satellite galaxies, from relatively large companions down to ultra-faint dwarfs. Each satellite feels Andromeda's pull and orbits accordingly, but the interaction is not one-sided. The satellites also tug back, raising tides in Andromeda's disk and halo. Over time, those tides can warp the outer gas, thicken the disk, and generate ripples in the stellar distribution. As a satellite plows through the halo, it experiences something called dynamical friction. Its gravity focuses background stars and dark matter slightly behind it, like a wake. That overdensity pulls back on the satellite, robbing it of orbital energy. The satellite slowly spirals inward, its orbit shrinking over billions of years. At the same time, tidal forces from Andromeda strip stars and gas from the satellite, stretching them into long streams that wrap around the larger galaxy. We see many such stellar streams in Andromeda's halo, each one the decaying orbit of a smaller system that is being digested. On an even larger scale, gravity binds Andromeda, together with the Milky Way and a few dozen smaller galaxies, into what we call the local group. The two heavyweights, our galaxy and Andromeda, dominate the group's gravity. Measurements of their relative motion show that Andromeda is moving toward us at roughly 110 kilometers per second along our line of sight. That is faster than any space aircraft we have ever built by a huge margin, but the distance between us is so enormous that this closing speed still implies billions of years before a direct encounter. There is almost certainly some sideways motion as well, a tangential component we have only recently begun to measure with any confidence. That sideways motion will change the exact details of the future orbit, the angle and timing of closest approaches, and how many passes the galaxies make through each other before finally merging. But as long as the total energy of their relative motion is negative, meaning they do not have enough kinetic energy to escape each other's gravity, a merger is guaranteed. They are like two skaters on a frozen lake tied together by a long rope. No matter how they spin and circle, they are stuck together in the end. Inside Andromeda right now, gravity is also quietly deciding the fate of individual stars and clusters during that future encounter. Stars on certain orbits will be more easily flung out into long tidal tails when the Milky Way swings by. Others are so deeply embedded in the central potential that they will remain bound no matter how chaotic the interaction becomes. Some globular clusters will be stripped from their current orbits and reassigned to new paths in the merged system. In that sense, the orbits you could calculate today already contain information about where those stars and clusters will end up in the future combined galaxy. If you think about it this way, Andromeda is not a static picture at all. It is a constantly updating solution to a gigantic gravitational problem. Every orbit, from a star near the center to a dwarf galaxy in the halo, is a line being drawn by gravity over cosmic time. The disk is held up by the compromise between rotation and collapse. The spiral arms and bar are standing patterns in a sea of moving stars. The halo streams are the stretched-out remains of old companions. The approach toward the Milky Way is just the largest scale example of the same rule. Mass attracts mass, patiently, relentlessly. In the next part, we will step outside Andromeda completely and look at its extended family in the local group, compare it to the Milky Way, and see how these two great spirals fit into the wider hierarchy of galaxies in the universe. Andromeda is not drifting through space alone. It sits at the center of a loose swarm of much smaller galaxies, each one a collection of stars and dark matter with its own history. Some are already half digested, some are still on long looping orbits. All of them feel Andromeda's pull. When you picture this galaxy, it helps to imagine not just the bright spiral, but a cloud of faint companions around it, slowly being herded and sometimes torn apart by gravity. This is what galactic cannibalism looks like up close. Astronomers have catalogued at least a dozen satellite galaxies clearly bound to Andromeda, and there are likely more that are too faint for current surveys to see. These satellites come in several flavors. The larger ones are dwarf spheroidal or dwarf elliptical galaxies, containing a few billion stars and very little gas. The smallest are ultra-faint dwarfs with only thousands or tens of thousands of stars spread through a surprisingly large volume. In many of these tiny systems, dark matter outweighs visible matter by hundreds or thousands to one. They are almost pure dark halos with a sprinkling of stars, making them valuable laboratories for studying dark matter in extreme conditions. Two companions stand out because of their brightness and proximity. The first is Messier 32, often shortened to M32. It is a compact elliptical galaxy that sits almost on top of Andromeda in our sky, only about 24,000 light-years from the main galaxy's center in three-dimensional space. That is practically touching by galactic standards. MER 32 measures roughly 8,000 light-years across and contains several billion stars. Despite its modest size, it hosts a supermassive black hole of a few million solar masses at its core, similar in mass to the black hole at the center of the Milky Way. M32's compactness and central black hole hint at a more dramatic past. One leading idea is that it used to be a much larger galaxy that ventured too close to Andromeda. Tidal forces would have stripped away its outer stars and gas over repeated passes, leaving only the dense central core behind. That core is what we now see as M32. Meanwhile, the stripped stars have been incorporated into Andromeda's halo and disk, their original identities erased. In that sense, M32 may be the fossil heart of a once respectable galaxy that fell victim to its bigger neighbour. The second well-known companion is Messier 110, or M110. It is a dwarf spheroidal galaxy orbiting farther out, roughly 170,000 light-years from Andromeda's centre. M110 is elongated, with streams of stars extending from it that are visible in deep images as faint arcs linking it to Andromeda. Those streams are the clearest sign that M110 is in the process of being torn apart. Star by star, its outer layers are being pulled away and stretched into the halo. Given enough time, M110 will likely be completely disrupted, its stars indistinguishable from the rest of Andromeda's halo population. Beyond these two lie many smaller satellites. Some, like Andromeda 2 or Andromeda 7, are classic dwarf spheroidals, dim puffs of old stars with no gas and little ongoing star formation. Others are ultra-faint dwarfs, so dark matter dominated that their stars barely register in surveys. In these tiny systems, the gravitational pull of dark matter is the main thing holding them together. Because they are so delicate, they are easily disturbed. A close passage by Andromeda can strip away large fractions of their stars, leaving even fainter remnants behind. One of the most intriguing features of this satellite swarm is that many of the companions are not scattered randomly in all directions. Instead, a surprising fraction lie in a thin, extended plane and seem to share a common sense of rotation. It is as if a significant portion of Andromeda's satellites have lined up in a spinning disk-like structure of their own. This planar arrangement puzzled astronomers when it was first recognised. In simple versions of our standard cosmological model, satellites tend to be more isotropic, sprinkled more evenly around their host halos. Over the past decade or so, a likely explanation has emerged. The planar satellites may be the shredded remains and surviving cores of a single large galaxy that collided with Andromeda long ago. When a substantial intruder falls in, it is torn apart by tides, its material stretched along its orbit into streams and smaller clumps. Some of those clumps can become tidal dwarf galaxies, small systems born out of the debris of a larger one. Because they inherit the original orbit of the intruder, they naturally share a common plane and sense of motion. In this picture, the satellite plane is not an anomaly at all, but a lingering signature of a major merger between 8 and 10 billion years ago. We see the debris of that and other events all across Andromeda's halo. Deep surveys, such as the Pan-Andromeda Archaeological Survey, have mapped sprawling stellar streams, shells, and over dense regions wrapping around the galaxy. Each features the ghost of a galaxy or globular cluster that came too close and was dismantled. By tracing the paths of these streams, astronomers can reconstruct the orbits of past satellites and the shape of Andromeda's gravitational potential. The emerging picture is of a galaxy that has grown substantially through the steady consumption of smaller systems. Now pull the camera back even farther. In the local group, Andromeda is one of two giants, the other being the Milky Way. Both are barred spiral galaxies with central bulges, extended disks, and large halos. Both host families of satellite galaxies, yet they are not quite twins. Andromeda's disk is larger in diameter, roughly 1.5 times that of the Milky Way on current estimates. It contains perhaps 2 or 3 times as many stars. When astronomers add up the mass of stars, gas, and dark matter, they find that Andromeda weighs in at something like 1.5 to 2 trillion times the mass of the Sun, while the Milky Way likely sits between 1 and 1.5 trillion solar masses. There was a brief period when some studies suggested our galaxy might be the heavyweight, but more recent work has shifted the balance back in Andromeda's favour. Andromeda's stellar halo is also more extended and more clumpy than the Milky Way's. It shows stronger evidence of past violent mergers with prominent streams and shells. The Milky Way has its own ongoing meal in the form of the Sagittarius dwarf and other smaller systems, but Andromeda seems to have had an even rougher history, swallowing larger companions and stirring its outskirts more dramatically. Despite being larger and apparently more experienced at cannibalism, Andromeda is currently forming new stars at roughly the same rate as the Milky Way, about 1 sun's mass per year. That parity hints that Andromeda may already have passed through its most active star-forming phase, and is now sliding toward a slightly quieter future. Within the local group, these 2 spirals sit at opposite ends of a roughly dumbbell-shaped distribution. Around each of them swarm their own families of satellites, and between them size a smaller but still significant galaxy, the Triangulum Galaxy, also known as M33. Triangulum may itself be loosely associated with Andromeda, possibly orbiting as a more distant companion, though the exact nature of that relationship is still under study. Together, Andromeda, the Milky Way, Triangulum, and dozens of dwarfs form a bound island of matter drifting through intergalactic space. Beyond the local group lie larger structures, galaxy clusters, and filaments of the cosmic web, but on the scale of tens of millions of light-years, the local group is its own coherent community. Within that community, Andromeda is not just a solitary spiral, it is a central actor. Surrounded by smaller galaxies, it is slowly consuming, facing another giant that it will one day merge with, and embedded in a dark matter halo that binds the whole ensemble together. In the next part, we will finally follow that looming encounter forward in time. We will watch Andromeda and the Milky Way fall together, collide, and eventually merge into a single new galaxy, and we will ask what that transformation means for stars, planets, and any future observers who might be there to witness it. Right now, Andromeda looks peaceful, a faint patch in the sky, slowly rising and setting as the Earth turns. But in reality, that entire galaxy is on a collision course with us. Our Milky Way and Andromeda are not drifting apart into the cosmic dark. They are falling toward each other under their mutual gravity. The motion is slow on human timescales, but relentless on cosmic ones. In this part, we are going to time jump into the future and watch what happens when two giant spiral galaxies meet, pass through each other, and eventually merge into one new system. First, the setup. Today, Andromeda is about 2.5 million light-years away and moving toward the Milky Way at roughly 110 kilometers per second along our line of sight. That speed is staggering compared to anything we can build. Yet the distance is so vast that it will take billions of years before the real fireworks begin. Simulations suggest that in roughly 4.5 billion years, Andromeda will have crept close enough that it fills a huge swath of our night sky. Instead of a small smudge, it will stretch across it, its spiral arms clearly visible to anyone with eyes and a clear view. Calling what happens next a collision is both accurate and misleading. The two galaxies will interpenetrate each other, their disks passing through like overlapping ghostly pinwheels. But the stars themselves almost never collide. Space inside galaxies is mostly empty. The typical distance between stars is many trillions of kilometers, while the stars are only a few million kilometers across. The chance that two individual stars hit each other head-on is vanishingly small. The real impact is gravitational and gaseous. As Andromeda and the Milky Way interleave, their gas clouds do collide. Vast clouds of hydrogen and molecular gas slam into each other, compressing, heating, and triggering intense bursts of star formation. For a brief era, the merged system lights up with swarms of hot blue short-lived stars. These baby giants carve out cavities in the gas, blow bubbles with their stellar winds, and then end their lives as supernovae, pumping more energy and heavy elements into the surroundings. The calm spiral patterns we see today give way to a chaotic, knotted, brilliantly lit structure. Gravity also goes to work on the stars and dark matter. The smooth, nearly circular orbits that stars follow now are disrupted as the combined gravitational field becomes lopsided and time-dependent. Tidal forces pull out long tails of stars that stream away from the main bodies, creating spectacular arcs stretching hundreds of thousands of light-years. Some stars gain enough energy in the chaos to escape entirely, becoming intergalactic wanderers drifting through the void with no galaxy to call home. Others sink deeper into the combined potential, their orbits shrinking toward the center. The encounter will not be a single pass. The first close approach slows both galaxies and flings out tidal tails. But momentum carries them through each other. They separate again, still bound like two dancers who have swung around and released their grip for a moment. Gravity then pulls them back for a second pass, then a third. With each encounter, more orbital energy is converted into internal motions, into the random jumbling of stellar orbits and the heating of gas. Over the course of several billion years, the two spirals lose their separate identities and settle into a single merged system. Deep in the core of each galaxy, another drama unfolds. Both Andromeda and the Milky Way host supermassive black holes at their centers. As the merger progresses, dynamical friction causes these black holes to sink toward the new common center. They form a binary pair, orbiting each other while surrounded by a dense swarm of stars. Over time, interactions with those stars and with gas drain energy from the binary, bringing the black holes closer. In the final stages, they radiate enormous amounts of energy in the form of gravitational waves as they spiral together. That last step, the actual merger of the two supermassive black holes, will produce one of the loudest gravitational wave signals in the history of the local group. Space and time themselves will ripple. If there are highly advanced observers around at that era with sensitive detectors, they will be able to reconstruct the masses and spins of the black holes and test general relativity in conditions far beyond anything we can reach. When the event is over, only a single, even more massive black hole will remain at the heart of the merged galaxy. What will that final galaxy look like? Most simulations suggest that it will be a large elliptical or lenticular system rather than a classic spiral. The orderly rotating disks of the parent galaxies will be scrambled by the violent gravitational interactions. Stars that once orbited in a flat plane will be scattered into orbits pointing in many directions. The result is a roughly spheroidal distribution of stars with little or no spiral structure. Astronomers have jokingly dubbed this future system Milkdromeda, or sometimes Milkomeda. It will likely contain almost all the stars that currently belong to the Milky Way and Andromeda, plus the remains of many satellites. Star formation in Milkdromeda will probably decline over time. During the merger, gas is driven toward the centre and consumed in intense bursts of star formation. Some gas is heated and blown out into the halo, or even beyond, making it harder for it to cool and form new stars later. The new galaxy may end up with a large population of old red stars and only modest ongoing star formation. In the far future, as remaining gas is used up or locked away, Milkdromeda could become one of those red and quiet galaxies we see in other parts of the universe today. What about our own solar system during all this? Long before the merger, the Sun will have evolved off the main sequence. Around 5 billion years from now, it will exhaust the hydrogen in its core and expand into a red giant. That phase alone may strip Earth of its oceans, atmosphere, and perhaps even engulf our planet entirely, depending on details of mass loss and orbital changes. The fate of Earth is grim regardless of what Andromeda does. The larger cosmic light show will be unfolding in a sky above a world that is no longer habitable in any familiar sense, if the world exists at all. Still, it is worth imagining the view if some observer, somewhere in the local group, does manage to witness the merger from a safe distance. Over many millions of years, the night sky would change from a band of the Milky Way plus a faint Andromeda smudge, to a double spiral looming huge and distorted, then to a tangled web of tidal tails and starburst knots, and finally to an enormous, smooth, star-filled glow. The story of Andromeda and the Milky Way is not a slow slide into darkness. It is a transformation, a long dance that ends in a new kind of structure. In the next part, we will pull the camera even farther back. We will compare Andromeda to the biggest galaxies out there, think about where it fits in the cosmic hierarchy, and confront a strange fact about all our observations: we never see Andromeda or anything else as it is now, only as it was long ago. By now we have dissected Andromeda from many angles. We have talked about gas and stars, black holes and dark matter, streams and satellites and future mergers. Yet the most haunting part of this galaxy is not what we see. It is what we cannot see at all. Hidden inside that faint patch are worlds we will never image, possible ecosystems we will never sample, and maybe even minds that will never know we exist. In this part, we are going to stand on the edge of what astronomy can do and look out across the gap between what is knowable and what will always be speculation. Start with something simple and concrete. Planets. Andromeda contains roughly 1 trillion stars. If planet formation in that galaxy is anything like what we see in the Milky Way, then most of those stars probably have planets. We know from exoplanet surveys in our own galaxy that planets are common. Tiny rocky planets, hot gas giants skimming their host stars, cold distant worlds. Whenever astronomers point precise instruments at a large sample of stars, planets turn up everywhere. There is no good reason to think Andromeda is different. Statistically, it should host billions or trillions of planets circling its suns, yet we cannot see a single one of them. The techniques we use to discover the planets in the Milky Way rely on tiny effects. A star dims by a fraction of a percent when a planet passes in front of it. Or its spectrum shifts back and forth as the planet's gravity tugs on it. At Andromeda's distance, these signals are simply too small. The star's light is faint. The angular separation between a planet and its host star on the sky is far smaller than what even our most powerful telescopes can resolve. Individual asteroids, moons, and comets are beyond hopeless. As far as our instruments are concerned, Andromeda's planets do not exist. We cannot detect their atmospheres or search for chemical hints of life. We cannot see continents or oceans. We cannot count moons or rings. All of the rich detail that we dream about when we picture alien worlds is sealed away behind distance and physics. Even the James Webb Space Telescope, with its exquisite sensitivity, cannot pick out an Earth-sized planet around a single star in Andromeda. It is like trying to watch a firefly orbit a lighthouse from across an ocean. So we fall back onto statistics, and on the one example we know well, Earth. Here, life appeared early in the planet's history. The oldest hints of biology date back over 3.5 billion years. That is not long after the surface cooled enough for liquid water to be stable. This suggests that once you have a rocky world in the right zone with water and a few energy sources, chemistry may be eager to climb the ladder toward life. If that is true in general, then many of those invisible Andromedan planets could host simple organisms, microbes in oceans and lakes, colonies in subsurface oceans under ice, tiny ecosystems in clouds or near hydrothermal vents. Intelligent life is another step entirely. On Earth, simple life dominated for billions of years before anything complex appeared. Multicellular animals with nervous systems and senses are a very recent invention. Technological civilization is newer still, arising only in the last thin sliver of Earth's history. If intelligence requires a specific chain of unlikely events, it might be very rare. There could be countless living worlds in Andromeda, and only a handful where anything like a brain has ever evolved. Or perhaps intelligence pops up often, but tends to burn itself out quickly with its own technology, leaving behind a galaxy full of fossils and none of the builders. This is where the famous puzzle known as the Fermi paradox sneaks in through a side door. When you take galaxies like Andromeda and ours and fill them with planets, it is tempting to assume that someone out there should have spread, signaled, or at least left obvious traces. Yet as far as we can tell, the sky is quiet. In radio surveys, Andromeda is a source of natural emissions from cosmic rays and gas, not a glaring beacon of artificial transmitters. Its light looks like the combined output of stars and dust, not a galaxy wrapped in engineered structures. That silence can mean many things. Maybe civilizations are rare. Maybe they stay local and do not announce themselves. Maybe their signals are short-lived. Or maybe we simply do not know what to look for. Whatever the answer, communication with Andromeda is effectively impossible. Even at light speed, a message takes 2.5 million years to cross the gulf. A reply would take another 2.5 million years to come back. Information would crawl back and forth over timescales longer than the entire lifetime of our species so far. Any conversation would be carried on by civilizations that have no continuity with the ones that sent the first messages. They would be different beings asking different questions. From any practical point of view, Andromeda is beyond talking distance. There is another limit built into the situation. When we look at Andromeda, we are not seeing it as it is now. We are seeing it as it was when that light left, 2.5 million years ago. In that time, Andromeda has continued to evolve. Stars have formed and died. Supernovae have gone off. Whole star clusters have shifted along their orbits. If life exists there, it has had millions of years to change. Maybe across those epochs, some species learned to use tools, or burned itself out, or built a technology we would not recognize. We will not know until their light finally reaches us long into our future. The present day Andromeda is always ahead of what we see. The same is true in reverse. If someone in Andromeda is looking at the Milky Way right now with a giant telescope, they are not watching our current world. They see our galaxy as it was 2.5 million years ago. No cities, no radio, no telescopes pointing back. On Earth, early human ancestors are just beginning to use stone tools. From their vantage point, we do not exist yet. Our entire recorded history, every civilization, every telescope that has ever stared at Andromeda, all of that is still in our future as far as their image of us is concerned. Put these facts together and you get a strange feeling. Andromeda is close enough to resolve individual stars, close enough to map in detail, yet forever out of reach for direct exploration or communication. We can measure its mass to a few percent and still know nothing about the layout of a single forest that might or might not be growing on a rocky moon there. We can simulate its future merger with our galaxy and still be completely ignorant of whether any minds inside it will be there to watch. And yet, this is not a reason for despair. It is part of why astronomy is so powerful. We are forced to work with incomplete information, to squeeze as much meaning as we can from light that has travelled for millions of years. That constraint pushes us to be clever, to invent new telescopes and new ways of interpreting the photons we catch, to test our ideas against the little we can see. The limits themselves become engines of creativity. In the final part of this journey, we will step back one last time. We will place Andromeda alongside the largest galaxies in the universe, confront just how small even this giant really is, and then bring the focus all the way back down to you on your tiny world, thinking about all of this before sleep. Stand outside on a clear night and find that soft, hazy blur in the constellation Andromeda. To your eyes it is fragile, almost shy. a thumbprint of light on the black paper. Now layer in everything you've learned on this journey. You're not looking at a smudge, you're looking at 1 trillion stars bound together by dark matter, threaded with magnetic fields, lit by nebulae, wrapped in streams of cannibalized galaxies, and on a slow collision course with your own cosmic home. That faint glow is one of the most complicated objects your brain has ever tried to hold in mind. Even so, Andromeda is not the ultimate giant. Far away in rich galaxy clusters, enormous ellipticals lurk, such as IC1101 in the Able 2029 cluster. Galaxies like that may contain tens or even hundreds of trillions of stars. Compared to them, Andromeda is merely big, not absurd. And even those titans are only small nodes in a much larger pattern, the cosmic web, a vast network of filaments and clusters stretching across billions of light years. Zoom out far enough and Andromeda becomes a dot, then less than a dot. This is the hierarchy you live in. A person on a planet, orbiting a star inside a minor spiral galaxy, which is one of a few dozen galaxies in the local group, which is a tiny part of a supercluster, which is one thread among many in the cosmic web. On the scale of that web, Andromeda and the Milky Way are just a double speck, to 2 grains of luminous dust drifting in a dark room. You might expect that to feel crushing. Sometimes it does. The numbers are too large, the distance is too vast, the time scale's too long. 2.5 million years for light to make a single trip, billions of years for galaxies to collide, trillions of years for red dwarfs to burn out. Against that background, a human life is a flicker. A civilization is a brief glow. A whole recorded history is a thin scratch on a cosmic timeline. From one angle, the universe is telling you a blunt story. You're small, yet there is another angle. Out of all the atoms in Andromeda and the Milky Way, only a minuscule fraction have ever been arranged into something that can think about galaxies. Most atoms spend their entire existence locked in gas and dust, in the interiors of stars, in the cold dark between systems. They never notice where they are. They never ask what it means. You're made of the same raw material, but arranged in a way that lets you understand that raw material. The iron in your blood was forged in ancient stars. The calcium in your bones formed in stellar cores. The oxygen you breathe was cooked in massive stars and spread by your supernova explosions. The atoms in you are not visitors in the universe. They are the universe, temporarily configured into a pattern that can look back and say, I see Andromeda, I understand what it roughly is. The true scale of Andromeda is not just a set of statistics written in an astronomy paper. It is the gap between one person standing under a night sky and a galaxy so large that light needs longer than human history to cross it. It is the knowledge that this galaxy has existed for roughly 12 billion years, will exist for billions more, and yet you get to share a few decades in which you can know its name, trace its outline with a fingertip, and follow photons from it into your eyes. There is also a kind of strange intimacy here. Andromeda is not just a random distant object, it is our nearest giant neighbour and our future partner in a merger. The same gravity that keeps you on the ground is, on a different scale, pulling the Milky Way and Andromeda together. The atoms in your body are caught up in that long-range embrace. You are falling toward Andromeda right now, very slowly, as part of the Milky Way. When those 2 galaxies finally merge long after the sun has finished its life, some of the matter that once made you will be part of the combined system. Think about what you have done over the course of this journey. You've ridden a beam of light for millions of years in imagination. You've walked across a galactic disk that would take longer than human existence to cross even at light speed. You've watched stars leave and die, seen black holes sleep and occasionally flare, traced the paths of satellite galaxies as they are torn apart, and watched a future galaxy form from the crash of 2 spirals. All of that happened using nothing more than a thin stream of photons, some physics, and a brain that fits inside a skull. That is the quiet miracle hiding in all these numbers. The universe is large, yes, but not incomprehensible. With patient observation and careful thought, a species of primates on a small world has figured out what Andromeda is. They have measured its distance, mapped its spiral arms, weighed its dark matter, traced its streams, and predicted its future dance with the Milky Way. There are still mysteries, like the identity of dark matter and the true abundance of life, but the fact that you can even phrase those mysteries clearly is remarkable. So the next time you see that faint smudge in the sky, remember what it really is. A trillion suns, many with planets, star-forming rings and ancient bulges, ghosts of swallowed galaxies streaking through the halo, invisible magnetic storms and high-energy particles, a supermassive black hole quietly waiting at the center, a future collision partner for your own galaxy, a structure so large that crossing it is beyond the reach of any realistic technology, yet so well understood that we can write down its size in meaningful numbers. And then, bring your attention back down to where you are. A body lying in a bed on a small rocky world, held to the surface by the same gravity that shapes galaxies, breathing air made of atoms forged in stars. Your worries and hopes and plans exist on a completely different scale from Andromeda, but they are not trivial. They are what this particular arrangement of atoms does. The universe explores its own possibilities through structures like galaxies and through beings like you. Sleep, when it comes, will not change the motion of Andromeda or the future merger of galaxies. It will not speed up the light crossing millions of light years. Yet letting your mind drift with these scales, from your room to your planet to your galaxy to that soft blur overhead, can reshape how tomorrow feels. You wake up still small in size, but with a larger mental universe to live in. And that might be the most important scale of all.